everyone. My name is Mikhail Roshkov. I am co-organizer of Meetups ML Repa community, and welcome to our meetups. And today we have a special guest, Liran Nahum from Superwise.ai. He's a senior data scientist, and today he'll talk about monitoring in machine learning. And actually, this is the first international meetup for ML Repa. So let me just explain what is ML Repa and what we are talking about. So we started our meetups 1.5 years ago, and we talk about different problems in machine learning engineering. Is reproducibility, experiments management, and pipelines automation. So there are a few topics we usually talk about. Is how to manage our experiments and in machine learning and how to make them reproducible, how to deal with data and model files, how to version them, how to manage them and store, how to enhance teamwork and collaboration for machine learning projects, and also how to build CI/CD pipeline architecture and get everything automated if we can. So all these topics we are welcome, and if you can give a talk on any of these or related topics or any engineering tools that can help teams in machine learning projects. So we are welcome to host such kind of events, meetups, or tutorials, workshop, whatever. So if you're interested, just let me know and we can talk about this. So this is a simple introduction about MLRepa. So now please, Liran, you may start. It's your time.
No problem. Nice to meet you. I'm honored to be the first international meetup of MLRepa. Let me just do share. Okay, you see my screen, right?
Yes.
So we'll talk about monitoring machine learning, challenges and best practices. So a bit about us. I'm Liran. I have 7-8 years of experience in machine learning, both in enterprises and startups. In my previous job, I worked in a consulting company in this field of machine learning and data science, and also gave lectures and in courses of data science. And now I'm data scientist here in Superwise. Oren is the co-founder. He will join us in a minute or two. The co-founder of the company of Superwise.ai. So what we'll talk about today, we talk about why do we need ML monitoring, a bit about the ML monitoring approach, how do we measure drift, and then we give some guidelines and principles in ML monitoring, how can we leverage monitoring in our production environment. And if we have time, we'll show a short demo of our product and services. So a bit about us, Superwise.ai. What we do, basically, we aim to empower data science and operational teams with the visibility and control on their ML models in production in order to scale their AI activities. Now, why ML monitoring is important, or why is it important now? What has changed? Like AI adoption is not new. Everybody talks about it in the last 5, 6, 7 years. But what we do see in the recent year or two is there is a significant shift from working on a POC level to more massive scale in production. Now, a good analogy for that is the transition from hobby to mass production. It's the difference between building a furniture in your backyard manually when you give a lot of attention to each furniture you build, to building a production line that in a systematic way produce many furniture, fast, low uncertainty, high quality, and still keeping positive ROI. It's similar to this transition. And when we talk about the massive scale in machine learning, what we really care about is making the development process of machine learning models more faster and more efficient. Now, the whole process. Now, you probably know this diagram in different types. You also showed it in your MLOps presentation a minute ago. But there is main phases in the life cycle of machine learning model. There is the problem definition, there is the research, including development and testing, there is the deployment to production, and then the monitoring and maintaining it in production. Now, if you think about it, like the first 3 steps are limited by time and effort, it's not make them easier. Every step has its own challenges, but usually they are limited with time. While the last step, the monitoring and maintaining, it's an ongoing task. Of course, we back to the research and we improve and optimize and refit the model, but once we have a model in production, it's a continuous process of maintaining it and keeping it live, accurate, and valuable to the business. Another key important to notice is that for every step in the first 3, there is a different persona that's responsible on this step. The problem definition is done by the business side, the research and development is done by the data scientist, and the deployment is usually done by an engineering team. While the ownership on the last step is a lot of time not really clear who is responsible, who owning the models once they're in production. The ones that develop it, the ones that deploy it, or the business that are the users of the models. And a lot of the time, in many cases, the answer is all of the above. Everyone use it and everyone have a responsibility in maintaining the model. Now, keeping the model live, accurate, and valuable for over time, for a long time, it's a complex task. It's not easy as you think it first thought. And not only us saying that, also Google published a paper called Hidden Technical Debt, a famous paper, saying basically that maintaining models over time is difficult and expensive. Mostly because, for many reasons, but mostly because it's an ongoing task, continuing task in a dynamic environment that also other things may change. Now, what is ML monitoring? How do we monitor machine learning? So basically, first of all, machine learning system is as any other software system, and we need to monitor it the same way we monitor normal software systems. We need to monitor the memory, the CPU, logs, latency, and whatever we're monitoring using traditional IT solutions. But when we say machine learning monitoring, we usually focus on the decision making process, about the quality of the decisions. And there is 2 main approaches of how to monitor machine learning models. There's the black box and the white box. The white box, assuming we know the specific implementation of the model, it can be a regression regression or neural network or whatever, but once we know the implementation, we can monitor, like for example, for linear regression or logistic regression, we can monitor the coefficient of the model or neural network. Basically, we monitor the internal parts of the model. This can be easy to done for a specific, if you have a specific model that you use for all of your use cases and it's not going to change. but in many real-life use case, companies use different models. They change model over time. They use different models for different use cases, and it's problematic to develop the monitoring for each different model that we use. Compared to that, we have the black box approach. In the black box approach, we assume nothing about the implementation. We are agnostic to the specific implementation of the algorithm. What we care about is to see the data that we get into the model, the data that the model, the output data, the model send out, and we need to know the problem type, like its classification or regression. And what we do, we basically monitor the data in the flow of production. Basically, MLflow is taking the data from the features from the data sources, and can be different type of data. We send it to the model, get the output. The output can be decision probabilities for classification, can be numeric estimation for regression, or whatever type of output the model give us. And then we wait a bit, and then we get the label. Now, this is an important point that sometimes it's not trivial for people that didn't work in a production environment. In a research environment, we used to have all the data together, the input data and the labels. But in production, it's usually two separate processes. There is a process of prediction, of serving the prediction to the system, and there is a different separate process for collecting the labels. And usually there is a time delay between those. Once we have the labels, we can monitor also the labels and, of course, the model performance, comparing it to the model output. This way, we can monitor 4 elements in the flow of production, which correspond to different phases of the prediction. And monitor these 4 elements corresponding to 4 types of drifts that we want to monitor and want to detect when we monitor machine learning. So we go over them in brief. There is the concept drift. The concept drift is the intuitive drift when you talk about drift in machine learning. Concept drift is basically the drift in patterns, meaning the pattern has changed. If we use the same input, we get different output from what we used to have. And basically, it means that the model is not relevant. A good example for that is Corona. If you were searching for Corona in the internet a year ago, you'll probably get a beer result, while this day you'll get pandemic virus results. The other type of drifts are important, and they help us detect different types of changes. Basically, if we say that the concept drift, meaning that the pattern has changed and the model is not relevant, when we have the other type of drift, it not necessarily mean that the model is not relevant, but it usually say that the model is not optimized. We can have input drift when we see different input from what we used to have, from what we trained about. We can have inference drift, meaning the model has different decisions from what we used to see. And we can have a drift in the labels. Every one of them look at the data from different aspects and help us detect different types of drifts. With the distinguish that this one means that the real patterns behind the model is changing and the model is not relevant, as we said. And those one help us understand when the pattern stays the same, but the data that we see has changed and our model is not optimized anymore. Another note that it's important to talk about is, as we said before, label is not really available for us at real time, and usually it's tricky to monitor. usually there are different use cases regarding to label. We can have fast feedback, like almost real time. In cases of real time bidding, if you work in the ad tech industry, we predict if a user will click an ad or not, and we have pretty fast feedback, and we have the label in real time. In this case, we can monitor labels and content drift and performance, and it will be good monitoring method. But in most cases, this is not the use case. It's not what happened. Usually, we have a time delay between the prediction and the feedback and the label, or we don't have the label at all. Think about cases when we manually label our prediction, which can be expensive, so we won't label all the predictions, or sometimes it's not available at all. If we, for example, decline a transaction, we suspect it's fraud, or reject a loan approval request, we won't have a real label saying that if we right or wrong, we basically decline the transaction and we cannot know what is the real label. So while those drifts are sounds very intuitive and concept drift is the main thing that we want to detect, it's tricky and it's very problematic to rely on. What we mostly want to monitor is the input drift and the inference drift, because these are relevant and available at real time. And in most cases, they are very good proxies for concept drift and performance issues in the future. By the way, I didn't say it at the beginning, but if you have any questions, feel free to ask and stop, and don't wait for the end. So at this point, I will stop and ask if you have any questions. By the way, Oren joined us, so he will also keep an eye on the chat, so feel free to ask things on the chat.
Liran, can I ask you a question?
Yes, of course.
Is our last slides about general approach of monitoring? And if yes, are you going to tell us about assuming specific model approach?
Yes, so we'll focus on the black box approach, which is better for using for scale with the use case with many models implemented, many different models.
But will you make some examples about specific models approach?
So I think that Liran is really focusing on how to approach a black box kind of monitoring. White box approach, it's really depend on the specific type of model that you're implementing, meaning how to monitor a naive base is one thing, how to monitor a logistic regression model is a bit different, but from our experience, we think that the black box approach is much more practical because most of the value in monitoring models comes through monitoring the data. And while white box approach means that once you change the model, you need to change your monitoring approach, black box monitoring approach doesn't need that, doesn't assume that. So you could still get the 90% of value by monitoring the data without being dependent on a specific implementation. And Liran will just now show how to monitor the data, meaning how to measure drifts in several techniques.
Okay, thank you very much.
So we mentioned different type of drift. So how do we measure drift? If we want to measure the constant drift, so the straightforward approach is measure the performance with the assumption that if we have a performance decrease, so the model is less relevant. Other things that we can measure is like measure the correlation between the features and the label, and if there is change in the correlations. So there probably also have a concept of changing the patterns. We can also compare it to offline or online benchmark model. This is a very common practice in research and offline work, but it's barely been implemented in online mode. However, when we want to measure a label drift, as we said, it's not necessarily mean that the model is not relevant, or we may not experience any, wait a second for, okay. We won't necessarily experience a performance drop, but it can be mean that our model is not relevant anymore. And we have an example here, so it's just a mathematical example to for sure that label drift can be misleading if we trust only the performance drop. So in this case, we have a binary classification. The a priori, when we deploy a model, when we research is 50% for each class, and we have to choose between two models. It can be the top two models out of 20 that we checked. And this is the percentage accuracy for each class, and the overall accuracy is 70% for model A and 68% for model B. After a few months, we may see a change in the label drift, which means that we see only 25% of class 0 and 75% of class 1. And even if the model stays exactly the same about the performance for each class, the overall accuracy is changing, and now model B is better than model 1. And if we monitor only the performance, we won't see any drop in the performance of model A. It stays the same, although the environment has changed, and now we can have better model in our system. But as we said, measuring concepts, measuring performance and measuring labels is a tricky and cannot be relied on, mostly because of the time delay. And what we want to measure is the data drift. We want to measure the data that is relevant at real time. Now, data can come in different formats, and different formats require different measure. Basically, we want to measure different statistics for every type. For numeric, we probably measure the minimum value, the maximum, the average, the variance. For categorical features, we can measure a number of unique values, a number of new values that arrive in production, the most frequent value, or entropy that measure the distribution. And this is value that can measure over time. Yeah, so now, how do we measure the data in an ongoing environment in production? So what we want to do is to test our assumption. When we train a model, we basically encode the assumption of the data in the model. And we want to test that the assumption still exists. So we can calculate all the statistics we just mentioned using our baseline. And the baseline is a data set that represents the normal behavior that we expect to see. Usually, it's the train or test set that we use to train the model. We calculate the statistic on the baseline data, which will serve as a reference. And then in the production environment, we calculate ongoing statistic and compare this statistic to the one that we calculated in the baseline. Then we have a measure of the difference between the ongoing data and the baseline that we use to train the model. If we want to measure the general input drift, so there are several ways. basically what we talk about here is measuring statistics about features, about every feature, but we want also to measure the general data drift of for all features together. And there is several methods. There is in the slide the descriptions of every method, but we won't go through every one of them. I'll just talk about the general differences between the two types. So we can measure the univariate changes, like we said, measure every feature by itself, and then aggregate the measurement to a single aggregated metrics that represent the changes in the all data. The disadvantage of this method is that it cannot catch multivariate changes in two features that shift together. However, it's very simple to implement and highly explainable, and the explainability part is an important functionality that we want with our measuring method, and we'll talk about it in a second. If we want to measure multivariate changes, we can use different methods. We can do clustering based on the baseline and then assign ongoing data to the clusters and measure changes in the distribution. We can use discriminator that can help us that try to distinguish between ongoing data and baseline data, and if the discriminator succeeds to distinguish between the data points, meaning that there is a shift, there is something that distinguishes between them. You can use PCA autoencoder. There are several methods. The trade-off between those methods and the univariate is those are probably will catch more complex patterns, but will be harder to diagnose and understand the change. If we see that there is a change in the with autoencoder that can catch very complex patterns change, it will be very hard to understand that what has been changed. While using univariate aggregation, like measuring each feature by itself and aggregate them, if we see a change in the aggregated feature, like see that it's change in the global data drift measurement, we can look after that at the univariate calculation and see exactly what feature have changed and what has changed. Like the values are dropped or increased, there is more missing values, more outliers. We can measure all of these things and diagnose exactly what is the cause of the general drift. What can cause data drift? So data drift can be caused from really many type of reasons. From what we see, most of the reasons are not concept drift or changing the patterns that usually people are looking for. It's more, a lot of time is technical issues, deployment issues, changes in some technical components in other part of the pipeline, of the data source pipeline. It can be bad training data. Bad training data is, bad is a strong word, can be just not a representative training data. It can be changes in the product. We can have UX change in our product. It will affect the behavior of customers, and those are usually the main reasons that we see for changes. And concept of change that really change the patterns in the data and require us to research again and deploy a completely new model is more rare than people expect. What can we do if we detect drift? So there are different approaches, and it really depends on the type of drift that we detect and the use case. We can retrain the model. we can separate the model to ensemble of different models that treat different use cases. We can do post-processing tuning, adjust the threshold or calibrate the result after the model. Can do many steps, and of course, if we detect it's technical issue, so we just fix the technical issue. And that's why it's also important to understand what is the change and what the cause of the change, because if there is a technical issue, retrain the model will not help us, and we just need to fix a technical issue that happens. Any questions till now? No, okay. So let's give this is how we measure drift in the data, how we should monitor our models using the black box approach, what type of drift we want to measure and how to measure them. And now we talk about more general guidelines and principles regarding ML monitoring. So first of all, the difference between observability and overflow. What we did till now just measure the drift, and we can put it in a dashboard and provide a very important visibility to the teams that use the models. But if you want to monitor for changes, and take example, if you have one use case that you do with 100 customers that you deploy the model for each customer, and we have around 100 features, which is a very common use case, and we have customers with more than that. In a simple calculation, you get thousands of KPIs that you need to monitor. And when you monitor and look for changes in the data for each KPI, it's important to remember that also there is different examples, different type of changes. We can have a blip, and normally that happens for a short time. This one usually corresponds to a technical issues. We can have a change in the level of value, like the value is changing. This is now the new norm of the feature. We can have data that is just in the normal values, but out of the seasonality, of the normal seasonality. And it's important also to distinguish between these different type of anomalies, different type of changes. And looking for every type in all these KPIs, it's a bit like find Waldo. If we had more time, I'll give you a few minutes to see if you can find it, but we're a bit short of time. So you can look after it. We'll send you, of course, the presentation with all the slide that we also skip about. But the conclusion is that measuring everything and providing the visibility with a cool dashboard is not enough. It's important and practical tool, especially for diagnose events and anomalies that we find. But it's not enough to find and detect the changes, especially not to work in a large scale. Defining threshold by the user are also problematic, like we saw before. We can have changes which are inside the control threshold that the user can define, and also every feature have different scale and different variance and stability, and defining the right threshold for every feature is not really practical. And what we need machine learning and specifically time series anomaly detection service on top of all the measurement that we just extracted. A few other things that are important to note and we want to talk about is that machine learning monitoring it's not just a tool, it's requiring adoption of new practices. And we see this with a lot of customers that start to work with us. For example, there are customers that don't necessarily have a standard process for collecting and labels and storing them in the database. Usually it's done manually, ad hoc for a research environment. Not all customers have a standard process to collect the real labels and store them for later use. Another thing that we see it's important is that ML monitoring involves different stakeholders. The question, like we said before, who owns the monitor in production? It's probably all of the stakeholders with different aspects of the model. The data scientist is developing it, the engineering deploy it, the operational teams use the models, and the business just need to trust the models. And everyone should have the visibility of the models in order to trust the model more. Last point that we want to mention is that drift can happen in subpopulation. Measuring the data, as we talked earlier, is nice, but if we measure just the whole population, some of the drift can hide in subpopulation, and we see that in many use cases. This is a screenshot from our product, a real use case that happened to one of our customers. You can see a small change that is almost not noticeable when we look at the whole data, but when we split it to different segments and check the drift in different different market segment, you can see there is a significant change in one segment while there is no change at all in different segments. Cases like this usually dealt with in different ways. In this section, we can focus on this segment and understand the change, and maybe provide like a fixing, like with a fixing approach, post-processing fixing for this segment, or just the operational team that use the model should know that there is a change for this specific segment, and maybe the model is not very stable at this phase for this segment. Last thing is that we can use the monitoring to improve our all research and deployment process. We can gain a lot of insights from monitoring our data in production, insight that can help us build and train better models. Possible insights are when we should train our models. If we see a drift in the data, we should take, for example, the data up until this change point, taking data older than the change point of the drift. If we see like for example, change like that, there's a change point. So taking data for retraining that is older than this point will basically use non-relevant and old data. If we see changes like this, it is blip. We said it's usually associated with technical issue. So we might want to take the old data and just exclude these days because it's noise if we train the system with that. So we should see what change we have, the type of change, when the change happen. This all can help us if it's happened like in the general population, just a subpopulation, maybe we should split our model to different model for different subpopulation. And we can gain many insights from monitoring the data in production and using this insight in the research phase next time we deploy and optimize our models. So what companies do about machine learning monitoring? This is like a bit, this is the view that we see on the market and how it's doing. So we see 3 steps of maturity in the aspect of machine learning monitoring. There is the doing nothing part. Usually it's companies that are still in POC step, maybe deployed one model to production. Usually they don't even think or have plans for monitoring their models. And there is companies that use few models already in production, and those companies usually build an in-house solution, do-it-yourself using Grafana or Kibana or other IT visualization tools, or leverage features in machine learning infrastructure platform like DataRobot and SageMaker. And companies with many models in production, usually from different kinds and use cases and models used, using a dedicated agnostic platforms like us or other companies. And interesting thing that we see is that we see the shift. Companies are moving from not monitoring at all to doing something, some basic monitoring in-house solutions, to using dedicated platform. Most of our customers started with in-house do-it-yourself solution, and as the scale of the models increased, they looked for a more dedicated platform that support all the use cases. That's it. We want to show you a short demo, but for that, if you have any questions, feel free to ask. No. Okay, no question. We move to the demo. You can ask questions later. Thank you. I'm a course. You need to.
Can you give me permission to do the video?
1 second. I'm not. Michael, can you make Oren a co-host also?
Already.
Thanks. Can you hear me well?
Yes, it's okay.
Okay, so it's Oren. Together with Liran, I'm the co-founder and CTO of Superwise. So yeah, we thought that we will take advantage of the last 10 minutes, to present you a bit. Liran was talking from our experience in the market and from doing that for several years about how to build a monitoring solution. We want to show you a bit how we took all those practices and all those advices into a practical solution that could be monitoring as a service for any company that does machine learning at high scale. Okay. So before I will start, just one thing to understand regarding our approach, which is, by the way, really come together with what Liran said. We believe that monitoring should be as a service, meaning that it should be agnostic to the type of the model or the type of the platform that you build your models on. Because, as we move on and the machine learning ecosystem increasing, more and more companies are pushing forward the ML democratization, meaning that even inside the specific company, different teams could deploy models on different platforms. So we build our solution in a way that it could connect to any type of platform and any type of model very easily through APIs or file integration, meaning we just need to get the data that we need through a shared file storage. And once we loaded it into Superwise, our customers could extract all the insights and all the full observability on production and our monitoring on top of it through our very nice dashboard that I will show in a minute, through APIs, and also we can alert to your favorite channel like Slack and email. And I do want to say one word about API, regardless of us, the Superwise, and you will see it in a minute, that it's a very important thing, because once you have monitoring in production and you have the observability regarding how data behave from production, you actually could start and build better automation on top of it. Meaning you could start and build automation saying that once you do detect drift in specific feature, raise an alert to this specific guy. Or for example, once you do detect a general drift, automate a retraining pipeline. Or not even to automate the retraining pipeline, but you could also automate what is the historical data set that you want to use for this pipeline. So having the monitoring solution with the production KPIs and automating it on top of it using APIs is really, a real amplifier of the value that the monitoring solution could provide. Now, let's see the product itself. So we want to bring, one common truth to different stakeholders, as Liran said, both to the data scientist team, but also to the operational team. So we built a very nice dashboard so everybody could log in. And using our agnostic approach, you could see that we could monitor different type of use cases. It could be from a regression type of task to a binary estimation and binary classification, or whatever type of machine learning task that you're trying to solve. From one end, you will get all the data monitoring, as Liran said, monitoring the input, the inference, and the labels. And the performance analysis will be relevant based on the specific task that you are trying to solve, because specific performance metrics are different for regression than performance metric to binary classification. On top of that, you can see that we are agnostic to the serving platform, so some of the models can be deployed on AWS SageMaker, on Azure ML Studio, or just a custom Python-made serving them. If I would take deep dive into one of the models, so the nice thing is that in one place we provide what we call a model health indication, meaning in one place we provide a full observability regarding all the different issues that currently exist inside your model. So what we can see at the top is a timeline where the blue line is the most important performance metric for this specific task, which is in this specific task, ROC AUC. And on the red bars, we can see the number of issues that our system alerted on. Now, as Liran mentioned during the entire session, in many cases, the label or the feedback or the ground truth is really missing or could come in a very large delay. For example, in this long risk assessment use case, the feedback delay could be 30 days or even more. So it means that for at least 30 days, you could not really monitor the performance. The performance is missing. But you can see that then the issues that we are raising are based on the input drifts and the inference drift. So we will be able to alert in real time. And what you can see is that currently there are many alerts. And if we will look back, we could see that our alerts are really correlated to a drop in performance that's usually being discovered only after it's too late. So given this real-time alert mechanism that I will show in a second what exactly we alerted on, you could detect issues in real time instead of waiting for the business to be impacted. Now, if I want to investigate, okay, what are the alerts? You could see that we provide them in high resolution, as Liran said. We could detect that there is a general drift in the entire set of population, in the 100% of the data, but we could also detect in which specific subsegment, meaning in which specific subpopulation inside your data, there are issues and which subpopulation are still healthy. Those subpopulation could be derived from an operational team that come and define proactively what are the type of segments that we want to monitor, or some of the segments here were created automatically by our system, discovering that it's an interesting segment to track because it's a weak spot of your model or having some other biased performance metric. Now, if I want to investigate, okay, why do I say that currently there is a data drift inside my entire data set? So I will go and dive into the event itself. And I will see our event mechanism, meaning what we see is what we call the weighted data drift measure. Liran mentioned that there are many ways to measure drift. So what we did is we are measuring it on a feature level. Each one of the feature, we are measuring the drift relative to the baseline and measuring it for the entire ongoing time frame. But then we are also aggregating it into a multivariant view where we could just look on the general magnitude of drift inside the entire data set altogether while we are weighting the importance of each feature and its influence on the accuracy of the model. So instead of looking feature by feature, we could monitor the general weighted input drift to see whether there is an issue, and only then to go and deep dive to see what feature exactly was deviating. Now, not only that we provide all those metrics out of the box, but we also, Liran talked about the difference between observability and monitoring. So it's a nice thing that you could see all those KPIs, but we understand that you cannot really go model after model, KPI after KPI, and start define thresholds. What is the level of drift that is relevant for this specific use case that you want to be alerted by? So we provide embedded inside our solution also time series anomaly detection on top of each KPI. So we will be able to detect whenever the feature is whenever the drift is gradual drift, or whenever there is a blip, as Liran showed you, or whenever there is out of seasonality kind of an event. So in this specific case, you can see that our anomaly detection detected that there is an increase in drift in the general population, and in a click of a button, you could get all the information that you need in order to understand exactly what the drift is and how to take care of it. This is something that, again, besides of the ability to measure all those KPIs, we saw from our customers that usually it takes them hours and even days to investigate why there is a drift, because they need to collect all kinds of people together inside the room and start to investigate and start to go to SQL and to do all kinds of queries. So we can see that in one view, we can see that there is a drift. We can see all kinds of related metrics about it, and to do a root cause analysis and understand exactly why the drift caused by it. And you can see in a tree-map view all the set of features that exist for this specific task. The size is by the importance of each feature, and you can see in red what are the features that currently are drifting, causing the general data to be drifted. And in an additional button click, you could see how exactly the distribution look like relative to how it should have looked like, and understand exactly whether this kind of change is expected, it's not expected, maybe it's due to integrity issue, and to go back and take care of this event. So what I really did here is that in a very easy flow and a very efficient flow, I was able to investigate a real production issue to understand where exactly it happened and understand exactly why it happened. And then I could go back to the event and give a feedback to our system whether this entire event was a good catch or not. And if I want to close the event, I can do that also, providing feedback to our system to adjust the expected behavior according to the user feedback. So the important thing that I want to show in our system, or whenever you try to do it yourself, is that it's not only about measuring the stuff, but it's also about creating one place that everybody could analyze it very efficiently, and also being able to monitor it automatically and build automation on top of it, because without automation, you will just go lost between all the different KPIs, searching for general issues and not understanding exactly why they happened. So that's what we did. We built a very efficient flow to investigate issues, to understand them, and get back feedback to tune the system on top of it. And that's on top of, the general analytical environment where you could query the data directly from production yourself and get all the statistics about the data in production. You could check what is the time frame that you want to see, compare it to a different time frame to see how the input look like, how the inference look like, the model performance, the common model performance charts, and so on. The last thing that I want to show is our very unique data DNA or data profiling view, which is very unique to our solution. And I think it emphasizes well what kind of insight you could take out of production back to your research environment. Because give me a moment and I will explain you what exactly do you see here, because from first sight it looked a bit frightening, but after you will understand what you see here, you will get the understanding of how many insights can you take out of it. So this is a two-dimensional matrix where each day is compared to a different day, meaning if I'm standing on this specific coordinate, I'm comparing the data set that arrived on February 26 to the data set that arrived on February 20. And using our unique statistical measurement, we are measuring the distance between those two data sets. This specific distance is quite low, and therefore the color is quite white. So because every day is totally similar to itself, the diagonal is totally white. And now that we understand like the mechanics of the matrix, we can see that we could very easily extract a lot of interesting insights, like the fact that there is a clear seasonality, because after every 5 days, we have 2 days that look quite differently, but look very similar to the same 2 days a week before, because that's weekend and non-weekend, which is already a good indicator or a good something to think of whether we really want to separate this model into two different models, one model to weekends and one model to non-weekends. We can see that we had 2 days of a blip, what Liran called a blip. They were totally different than any other day, but then it went back. So meaning if I'm standing at April and I want to retrain my model, I better to exclude those 2 days, because those 2 days could only enter some level of noise into my training data set. Similarly, I could see that there was a change for a period of almost 1 month during April, meaning that during April, maybe we wanted to do a retrain or build a more specific model to this specific time frame, but once we are out of April and moving to May, we might want to exclude the data from the previous month because it was looking quite differently. And not only that you're seeing all these insights all together, but you could consume them through APIs, and we saw that our customers building automation through our APIs on top of it to build a better data-driven retraining strategies that yield better model results eventually in production. And there's a lot more here, but I think it's a good demonstration of some of the things that Liran said that are really important, and how we tackled it and how we implemented it into our platform. And I will stop it here. Any general question regarding what I've just showed, or if it made you, to have some thought about it?
So you had four types of observations at the start of the presentation. Probability of Y, probability of X, probability of conditional, probability of Y conditional to B, and you said that you will consider only first two, right? So this supervised demo wasn't considering cluster two.
Okay, so yeah, you are totally right. I do want to say that we think that the practical approach should be that usually the first two are more important, but there are cases where the level comes fast. For example, in EdTech, whenever you are building a real-time bidding, mechanism. It could be that the label, the feedback will come back seconds after you did the prediction. So in those cases, the performance metrics or the label drift could be relevant, but it really all is depend on the use case. As you can see in our full analytical environment, all the different phases are being monitored. Data is equal to inputs, meaning that you can see what is the level of drift in your inputs. You could see what is the level of drift in your outputs. In this case, it's only probabilities. And you can see what is the level of drift in your labels. In this case, it's default loan or non-default loan. So all of those three are the input, inference, and label. And the model is all the performance KPIs, where performance KPIs are the best indication for concept drift, detecting, that there is a drift in the performance level, meaning that maybe concepts has been changing. But again, concepts or label drift usually depend on label, and therefore, in most cases, are quite difficult to rely on.
But if I have several models chained together, these conditional drifts turns out to be a lot of metrics plots and a lot of data plots. And it's hard to see them, to analyze them separately. It would be easier to see one conditional plot if it is a chained models.
I'm not sure that I got you regarding what is a changed model, but I do really.
I mean, chained. They are one model depends on another and another.
See, some kind of an ensemble, like one model is the input for the other model, right? So this is a very good question, and the question I think is coming back to the user. What does he really want to consider as the atomic level that you want to monitor? Because if you're looking on a chain of models, so you could say that the atomic level is the entire set of chain models, and then you could only analyze the input of the entire chain and the output of the entire chain. Or you could say that you want to separate it into monitoring each model by itself. So it really is depend on you, what is the level of granularity that you want to get alerts on. Okay?
Okay.
Any additional question?
May I ask a question? Does your system can monitor only table data, or it can also can be applied for some deep learning models, or you have some this in future plans?
So we totally are able to monitor deep learning models because there's two ways that we can monitor that. Because one thing that deep learning could still work on structured data, right? You could take this structured data and build a deep learning model. But I guess you're referring more to cases like text or image, where like the raw data doesn't really mean something, and you're using an embedded layer of your deep learning model to really structure the data in a latent space. So for this specific case, not only that we support different data types like numeric, categorical, or binary, and others, we are also supporting a data type where we call it a vector, meaning that you could bring the entire embedding layer as a feature that we are starting to monitor. So that's one thing. The other thing is that if I will take a text, let's say a tweet classification kind of problem, like let's find the sentiment of the tweets. So you could bring the embedded layer as a feature to the model, but you could also extract yourself some kind of meta features which could be important to monitor on. Let's say the length of the tweet, let's say the language of the tweet. So you could, beside of us monitoring the embedded layer, we could also monitor all those meta features and to give you the insights regarding in which cases the model is underperforming or not.
Can you please?
Okay, thank you.
Can you please detail one more time how you track weak spots, and how can we use it?
Yeah, so weak spot, actually, it's a very advanced capability that we provide now to our customers. We are providing the customer the ability to define what is an interesting group for his opinion. For example, he could define that interesting group is a group which is no more bigger than 5% and has high error rate, or maybe a group that has high bias in our decision making. So the customer could define what is the KPI that he really search for interesting group at. Let's say that in this case, the KPI that the customer wanted is to see in which weak spot we have high error rate. So based on that, and based on the KPIs that we are collecting, our platform is searching in the high dimensional space for specific groups that are really biased for this specific KPI. So in this case, we can see that the overall error rate was something like 8%, but we found 4 weak spots where in each one you could see the size of it, which was, for this example, it was almost 5% size of subpopulation, but the error rate is almost twice as much as the general population. And not only that we are saying that there is such weak spot, but we are characterizing the exact weak spot. We are saying that it happens whenever use purpose is 99 and income is 5,000. So this is a really nice insight, because now the business team know what is the weak spot of this new shiny model that they got. The data science team could see whether they could try and improve in this specific case. And as I mentioned, you could say, okay, I want to configure it as a segment that I want to start and monitor through the entire system.
Thank you.
So I've got a question related to false positives. Like in real world, there is always something changing. And like depending on your threshold, you can get an alert like every minute, or you can get like no alerts at all. How do you set those thresholds when you alert for something or when you don't alert?
So just to make sure that I understand the question, you're saying when you do such kind of an alert, there is the danger of like alert fatigue, or providing a lot of alerts of something that
exactly.
is not very important. So there are multiple levels of how do we solve it. One level is that we are not monitoring, we do monitor each one of the features, but like the way that we configure the event mechanism out of the box is to monitor only the general data, meaning that not every specific feature drift will cause to an alert, only if there is a high drift in the specific set of features that are important to the accuracy of your model. So only if that happens, we will detect it. And the other level of how do we avoid alert fatigue is also how do you know what kind of threshold to put? Because in specific cases, it could be that the data is very stable. And in other cases, we have that the data by its nature is very noisy. So there is where we apply our intelligence, and we are applying a time series anomaly detection technique to detect what is the level of expected performance of the expected drift in your specific case. So you don't need to really define, fixed user threshold, but we analyze and understand what is the natural seasonality, what is the level of noise that we usually are being regular to expect to, and based on that, define the threshold dynamically.
Do you set threshold based on the amount alerts that you want to receive?
So the customer, I don't have it right now in the demo, but the customer could, I'm showing all the magic here, but I don't show you the backstage. So the customer could, configure itself and move the sensitivity according to the level of, let's say, alerts that you want to really accept. So we have customers that are more sensitive and want to detect any small type of drift and are putting our sensitivity into a more high sensitivity. And some customers that, are more limited with resources and are reducing the sensitivity level, so they will get an alert only for big changes. And that's on top of the fact that you could define your own user thresholds. That's always possible. But I'm showing like the out-of-the-box solution where we are detecting such threshold dynamically for you.
Got it. And another question, like when you trying to find something changed in some segment of your data, there is a multiple comparison problem. It means like when you slice your data kind of thin enough, you will definitely find some small segments with a lot of relative change.
You're totally right. So that's why we're talking about two types of segments. One type of segments is based on your domain knowledge, meaning you come and define your specific operational segment that you want to monitor. If that's, for example, a marketing, if that's a loan approval type of use case, so maybe you have a specific set of VIP customers that you know that you really must to make sure that they are working well. So one type of segment is user-based, meaning that you provide your domain knowledge to understand what are the cases that you want to monitor. The other type is the weak spot that I showed, and this is where we are investigating the entire combinatorial space and searching for those specific cases which are highly biased but stable regarding their bias, meaning it's not something ad hoc that we found, but a specific subgroup that constantly is highly biased regarding their performance or regarding the KPI that you are searching for.
Thank you.
Sure. I will just mention again, we will share, Liran will share with you all the stuff later. And if you have, any additional question or something that you want to, to follow up regarding our platform, we'll be very happy to connect and talk and discuss and maybe to show you the demo or something more specifically for you. So feel free to reach out after the meetup.
Cool. Thank you very much. Thank you very much. And I think that after the meetup, people will continue to discuss it and ask questions for you as well. So what's the best way to communicate with you? I mean, what channels? LinkedIn, Facebook, or you have any special communication channel?
So I think the best way will be LinkedIn. We will share with you our LinkedIn profile, so you could approach directly to Liran or myself and take it from there.
Okay.
Michael will share the LinkedIn profiles with you, and you will be able to publish it, right?
Yes, of course.
Great.
Okay, so thank you very much. Thank you very much for your talk, for your time, and see you next meetup.